And hello everyone, Paul here to run us through the review for oceanography. We have three chapters: the ocean floor, ocean water, and ocean life, and the dynamic ocean, which includes just a bit on beach erosion. So as usual, I've got the review over here, and I've got the notes over here. I'll be highlighting the notes as I go through this, and then I will upload the highlighted notes along with this video. So beginning with the ocean floor, we begin with a question about the four ocean basins, describing their characteristics, size, degree of tectonic activity, etc. There's the question right there. And of course, here's the answer right over here. Let me get my highlighter going. And so here we go, right? The Pacific, the Atlantic, the Indian Ocean, and the Arctic, right? The Pacific is the largest, the deepest, the most tectonically active. The Arctic is the smallest and the shallowest, and the Atlantic and the Indian are kind of in the middle somewhere. Honestly, if I put something on the test about this, it will likely be the Pacific or the Arctic, because the Atlantic and the Indian are just kind of there. I mean, they're nice, but they're just kind of there. So anyway, but there's the four ocean basins. Then I asked, what's the difference between an active and a passive continental margin, right? And that is right here. So remember that the continental margin is just where the land meets the sea, and there's two kinds: there's active and passive. We live on a passive continental margin. Passive continental margins are not associated with plate boundaries, right? We have the beach, but it's all the North American tectonic plate. On the other hand, if you go to Washington, Oregon, Northern California, somewhere like that, you're at the beach, but you're also at the edge of the North American tectonic plate, right? Right offshore there is the Juan de Fuca plate. We do have a couple drawings here of these, right? So this is a passive margin here with the shelf, the slope, the rise, right? And then the abyssal plain. So you've got continental crust out here, oceanic crust out here. This is what we have here off the west and east coast of Florida, for that matter. And then active margins look like this, right? They look a lot like an ocean continent convergent plate boundary, because that's what they are, right? And so you've got oceanic crust here, shoving underneath continental crust, melting, rising magma, volcanoes. The thing we kind of added here was the accretionary wedge down here, which is just this wedge of sediment getting scraped off of that oceanic crust. And of course, we'll talk more about that sediment later on. But anyway, there are some pictures of each of those just to help you kind of understand what's going on. And that's a PDF file right there in your study materials. You can find that no problem. Then some more specific questions about these things. For example, coming to the passive margin, I ask, okay, what are some of the characteristics? What's the continental slope? Continental shelf, and what are some of its characteristics? Here's a bit about that right here, right? The continental shelf is basically flooded continental crust, right? The ocean, or rather the underlying crust, doesn't really care where the beach is, right? So it's that gently sloping, relatively flat submerged surface right there from the shoreline outward. It is geologically flooded continental crust. It's not very deep. Don't memorize numbers. It's just not very deep. A lot of the ocean's productivity is here, right? This is the neritic zone that we talked about. And of course, all of the ocean's petroleum is there. And of course, those last two bullet points don't always play well together. The continental slope is that transition between the continental crust and the oceanic crust. There it is right there. It's not sloping very steep, but it does have these submarine canyons, these large canyons that are carved out by these underwater landslides that are known as turbidity currents. And then, of course, at the bottom of that slope is the rise. And if I come back to my PDF file, we can come back up here, shelf, slope, what we're talking about right now, that transition, and then rise right here, okay? Alrighty, let me see. Okay, so this is kind of fun. Questions 5 and 6 have the same answer, right? What causes what causes submarine canyons? Turbidity currents, right? Those underwater landslides. What causes the continental rise? Turbidity currents, right? Turbidity currents basically remove sediment from one place and put it in another. Where they're removing the sediment, that's making those submarine canyons. Where they're putting it, that's making the continental rise. I accidentally unhighlighted turbidity currents up here. Let's fix that. There we go. Okay, so once again, 5 and 6 have the same answer. turbidity currents, right? And of course, the reason I gave you those drawings is I asked you, okay, draw a passive margin, draw an active margin. Now, it's a multiple choice test. I can't ask you to draw anything, but I can, give you, wrong button, give you these drawings and ask you, don't label them and ask you, okay, what's this, what's that, what's the other thing, right? And so you'll be familiar with these drawings. You might see them again on the test. Okay, and I'm all the way, here we go. Okay, so some other things, let me see. 10 and 11, or rather 10, seamounts, guyos, and abyssal plains, right? I threw three things together here that maybe ought not have been thrown together, but that's okay. Seamounts are underwater volcanoes, right? And so if I come down here, we're skipping active margins. We're skipping active margins. The only thing I ask you to do is draw that, okay? We're skipping this and we're going down here. Seamounts and guyos right here, right? Both are underwater volcanoes, okay? A seamount is just a normal kind of underwater volcano with a conical shape and, what you would think of as being an underwater volcano. A guyo, on the other hand, is an underwater volcano but with a flat top, right? And that top has been eroded by wave action. We were in class, we did a whole thing about guyos and how they formed and things like that. So anyway, and then the abyssal plain is just basically the generic bottom of the ocean floor, right? It's not it's not a volcano, it's not a ridge, it's not a trench, it's nothing like that. It's just the bottom of the ocean, right? These large expanses. And of course, what they really are irregular volcanic rock that formed at a mid-ocean ridge that's now been covered with sediment and is remarkably flat. And so there we go. Okay, and then we had three different kinds of sediment on the seafloor, and here they are here. Right, there we go. And there we are. Terrigenous, biogenous, and hydrogenous, right? The prefixes are the thing here, right? Terra, earth, sediment derived from land, okay, or dry ground or earth or whatever. Biogenous, bio, life. This is sediment that is derived from the shells of living organisms. I'm going to go ahead and tell it to ignore the spelling mistake there because it doesn't know how to spell. It does not know how to spell biogenous, so let's ignore that. Anyway, so this is the shells of organisms. Technically, a clamshell is biogenous sediment, but when we say that, what we really usually mean is all those microscopic plankton things floating around, dying in their shells, settling to the bottom. And then finally, hydrogenous sediment is kind of the sediment equivalent of chemical sedimentary rock, right, where you have sediment precipitating out of seawater. So there we go. Okay, so that's the first unit of the oceanography. Let's move on to ocean water and ocean life, right? And so we come down here. It's just right next to the notes. Define salinity. Well, here we go, right? Simple enough. There it is right there. Salinity is the amount of dissolved solid in the water. The trick here is that it's not just salt, NaCl, right? When an oceanographer says salinity, they mean everything, right? And everything that occurs naturally is in seawater in some concentration or another. It might be measured in parts per billion, but it's there, okay? So the only trick there, like I said, is it's not just salt, it's everything, okay? Now, where does it come from? Well, it comes from two places, right? First of all, mostly it comes from chemical and physical weathering of rocks on land, right? So you break down rock chemically and physically, and that washes into the ocean where it accumulates, and hence you get salty water, right? At any given time, the rivers flowing into the ocean are mostly fresh water, but they do have a little bit of salt, and that salt accumulates in the ocean. And then underwater volcanoes also spew all kinds of weird exotic chemicals into seawater. And, that might not seem like much, but keep in mind the entire mid-ocean ridge system is one long underwater volcano. And so that's going to contribute quite a bit. The average open water salinity has not changed. It doesn't really change, not quickly anyway. So if we're adding a whole bunch of salt to the water every year, all the time, we need to remove it too, right? And so we remove salt two ways. First way is chemical precipitation, right? Make some chemical sedimentary rock or make some hydrogenous sediment. One way or another, get those chemicals to come out of that water. There's a number of ways to do it. We've talked about some of them. And then also all those organisms in the water making skeletons, all those chemicals got to come from somewhere, and where they're coming from is the water. And so these things balance out to give us a fairly consistent average open water salinity. Okay, so let's see. Okay, now 3 might seem weird because I just said, a pretty consistent average open water salinity. It is, but it's not the same everywhere, right? And as I did in class, different places have different salinities. And so how do we get the salinity of seawater to change locally, right? Not globally. Globally, it's pretty steady. Locally, okay? So here we go, right? Here we are, and here we are. Here's how you get seawater to change, right? Salinity. Now, the thing to keep in mind is that we don't change the salinity of seawater by adding or removing salt. We change the salinity of seawater by adding or removing fresh water. Okay, so if we add fresh water, that decreases the salinity. If we remove fresh water, that increases the salinity. So how do we add fresh water? And I should probably be putting little air quotes around fresh because it's not like distilled water, but it's, reasonably fresh. River runoff is one way, right? Rivers are mostly fresh water, mostly, okay? Glaciers melting. Glaciers are, water locked up on land. When you melt those glaciers, you're adding fresh water. Sea ice melting, right? If you freeze seawater, you make freshwater ice and you leave saltier water behind, right? So if I melt that sea ice, I'm adding fresh water and lowering the salinity. And also maybe obviously rain. Rain is fresh water. If it rains a lot, the salinity is going to go down. It's not as easy to remove fresh water from the ocean, but there's a couple ways. Evaporation will do it, right? Good hot day. When you evaporate water, you remove fresh water and you leave saltier water behind, okay? And in fact, that's how you turn salt water into fresh water, is you evaporate it and then you recapture the water vapor and now you've got fresh water. Or make sea ice, right? Remember what I said, if you freeze seawater, you make freshwater ice and you leave saltier water behind, right? And so there we go. So that's how we vary the salinity in the world's oceans. Okay, so another property of seawater, up here you can see we got salinity, temperature, and density, right? So there's salinity. Temperature. Is temperature next? Temperature's next. What is the main control on the ocean's temperature, right? And I probably should put surface temperature there because the main control is, of course, latitude, right? The further north, someone's calling me. I'm going to do this. There we go. So latitude, right? The further away from the equator you go, actually, that was a faculty meeting. I should go to that. Okay, pausing. Okay, one faculty meeting later, and I'm back, and we're working on the question number 4 here. And you notice my questions restart, and that's going to be annoying, but it's going to keep happening. You'll notice my questions here restart the numbering. Oops, sorry about that. But question number 4 here: what is the main control on the ocean's temperature? And that is, of course, latitude. The closer you get to the pole, the colder the surface water gets. The closer you get to the equator, the warmer the surface water gets. Simple enough. Okay, so in lower latitudes, how does the ocean's temperature vary with depth? And that's just right here underneath that. If I can get it to highlight, there we are. And so the idea here is that lower latitudes we mean by the equator, down by the equator. And there you have a thermocline, right? So there what happens is solar radiation heats the surface water, but it doesn't penetrate even nearly all the way to the bottom. And so that surface water is heated, but then you get a temperature change called a thermocline, and that deeper water then is unmixed and unheated and really cold, just above freezing. Near the poles, the water's just cold all the way up. You don't have that change in temperature that, once again, we call a thermocline. Defining density, remember that density is mass per unit of volume, right? It's how much does something weigh as compared to how much of it do you have. Is kind of, how quote unquote heavy is something. And we've been in and out of density all semester long, so I think we get this by now. And then I ask, okay, what are two things in the ocean that affect the water's density? And those two things are, of course, temperature and salinity, right? The warmer water is, the less dense it is. The colder it is, the more dense it is. The saltier the water is, the more dense it is. The more fresh it is, the less dense it is. So I'm messing around with trying to fix things that don't really need to be fixed. And so, of the two, temperature is more important. You have to change the salinity a whole lot to change the density. You really only have to change the temperature a little bit. Okay, and then what are two things that we just did that? And then we have a slew of definitions here that are related to our classification scheme for organisms. It is an ecological classification scheme, and here it is, right? And so let me make sure I got all of it. I do. Here it is right here. So let me highlight it. And so plankton are organisms that float as opposed to swim in the ocean. Phytoplankton can carry out photosynthesis. Zooplankton eat phytoplankton. There we have plankton. Okay. Nekton is anything that can swim. So fish, whales, dolphins, porpoises, sea turtles, things like that. Benthos are things that live in or on the bottom. If they're living on the bottom, they're epifauna. If they're living in the bottom, they're infauna. If we come back up here to epifauna, they're living on the bottom. If they can move around, they're vagrant. If they live attached, they're sessile, right? And so there is our ecological classification of organisms: plankton, phytoplankton, zooplankton, nekton, benthos, epifauna, infauna, sessile, and vagrant. I cover them all, and they're right there in the notes. Then we get into some things that control where organisms in the oceans live. And so I ask about the photic zone and what factors affect it. And so here we are, right? The photic zone is the upper part of the water column where sunlight penetrates. It depends on a number of things, right? Anything in the water is going to shallow up the photic zone. So sediment and plankton in the water make the photic zone shallower. Time of day matters, right? There's no photic zone at night, right? The sun is up, so there we go. Noon, it would be at its deepest. And then time of year also matters. In the summertime, the sun is not as high in the sky, and so it doesn't penetrate the water as much. Then we have the euphotic zone and the aphotic zone. The deal with the euphotic zone is just because you have sunlight doesn't mean you have enough sunlight to do photosynthesis. And so the euphotic zone is that portion at the top of the photic zone where not only is there light, but there's enough light to do photosynthesis. The aphotic zone is just kind of the opposite. There's no light, right? No light in the aphotic zone. Most of the water in the ocean is in the aphotic zone. Okay, so there we go. So photic zone, euphotic zone, aphotic zone. Then we have, we talked a bit about distance from shore as a controlling factor in controlling the distribution of marine organisms. And we had some zones here. Let me make sure I get them. Intertidal zone, wave wash tidal zone, neritic zone, and the oceanic zone. And here they are right here. And what we're talking about here is distance from shore, right? And so, there we go. And so the intertidal zone is just a zone between the high tide line and the low tide line, right? So it's not even underwater the whole time. The wave wash tidal zone is that zone right at the beach, right? When you go swimming, you're in the wave wash tidal zone. Go out from shore a little bit, and you're in the neritic zone. This is where you want to be in the oceans, right? The neritic zone is pretty near shore, and we'll talk more about this, but this is the highly, highly biologically productive zone. And then the oceanic zone is that deep water offshore, right? Okay. If I come back, 12 asks, why is the neritic zone highly productive? And here it is right here, right? Why does everything want to live in the neritic zone? Well, the water's not that deep. So most of the water is in the euphotic zone. So you can do photosynthesis all the way down. You have a lot of nutrients washing in from land. So you have two things, right? You have sunlight and you have nutrients, and that equals biology. And so you have a lot of things living here. Also, the bottom provides a nice place for benthic organisms to live that is not ridiculously deep and ridiculously dark and cold and stuff like that. So that neritic zone, that shallow water on the continental shelf, is really where you want to be in the world's oceans. Okay, then we talk about some water depth. There's some words that we use with respect to that, and here they are right here. Pelagic zone, benthic zone, and abyssal zone, right? Yeah, okay, so there they are. Anything living in the water at any depth is said to be living in the pelagic zone. Now, real oceanographers divide up the pelagic zone. We're not going to worry too much about that. Benthic zone is anything living in or on the bottom. There's that word benthos, benthic, same root word. So in or on the bottom. And then the abyssal zone is, of course, in or on the bottom, but in very, very deep water, right off the continental shelf, where it's dark and cold. And so you have very high pressure water, very low sunlight, not a lot of food. It's cold, etc. It's a very, very difficult place to live, but things do manage to live there. Okay, so there's the second chapter. Let's go on to the third, where I do not restart the numbering, so yay me. Dynamic ocean, moving some water around. Okay, what are some factors that affect surface circulation? Here they are right here, right? So the surface circulation in the world's oceans is, first of all, driven by wind, right? You get large-scale wind out there pushing the water around, right? The second thing is the Coriolis effect, which, let's see, Microsoft Word thinks I misspelled, but it does not have any options for me, so I don't think I did. Anyway, it's doing weird. Okay, I'm going to leave it. Anyway, Coriolis effect, of course, happens because the Earth is spinning. It deflects things in the northern hemisphere to the right and the southern hemisphere to the left. This produces generally clockwise circulation in the northern hemisphere and counterclockwise circulation in the southern hemisphere. The other thing, of course, is the continents, right? The water's not going to run up on land just because the Coriolis effect says it needs to be turning right. So the continents also affect the movement of this surface circulation. Okay, so let me see. What's the Gulf Stream? Here it is right here, right? The Gulf Stream is a very well-defined current that flows to the north from the south off the east coast of the United States. It goes all the way over into the North Atlantic. And where it moderates temperatures in England and places like that, and we will talk more about that here in just a second. In fact, let's talk about it now. How might ocean currents affect climate? Question number 16, and here we are right here, right? Warm water currents like the Gulf Stream, okay, tend to moderate temperatures, especially places like England and Northern Europe. England is not nearly as cold as it should be, given how far north it is, thanks to the Gulf Stream, right? London's climate is about the same as Atlanta, Georgia's, right? It's just not that cold there, and it's pretty dang far north. The Gulf Stream is helping that out a lot. The other thing is cold water currents are commonly associated with deserts. So you get, where you have deserts, you very frequently have cold water currents offshore. I don't think they're causing them, but they're associated with them, and they're certainly not helping any. Okay, let me see. So here we go. Question number 17, what is upwelling? What effect does it have on productivity? Here we are right here. Upwelling is bringing that cold, nutrient-rich water up to the surface, right? Remember that deep water is cold, and, it doesn't have a lot to eat, but it does have a lot of nutrients, right? Remember, food and nutrients are different things. Nutrients are fertilizer. You can't eat fertilizer, okay? But if you can bring that nutrient-rich water up, now you have nutrients and you have sunlight, right? And that's what upwelling is. Off the one way to do it is off the usually west coast of continents. You blow that surface water offshore that draws that deeper nutrient-rich water up into the euphotic zone, and it really, really increases biological productivity a lot, an awful lot. Okay, so question 18, what drives deep ocean circulation? Here we go right here. Let me make sure there's no more down there, and there's not. So there we are right there. This is a vertical circulation that's being driven by changes in the water's density, right? You make sea ice. That does two things, right? First of all, it removes fresh water. That makes that the water left behind is saltier and therefore more dense, and it sinks and works its way over the ocean floor. The other thing is you just froze that water. It's really cold, right? The water that's left over and isn't ice. It's really cold. And so you have very cold, very salty water that's very dense. And so now it sinks and it works its way over the bottom of the ocean. Sometimes it's called thermohaline circulation, which if you saw my lecture, you know is a word that I really like because it's very descriptive. Thermo, temperature, haline, salt, right? So it's a circulation pattern driven by changes in temperature and salinity. Okay, there we are. Water waves in the open ocean transmitting. Nothing on tides on the test, so don't worry about tides. Skip tides. Here it is right here, right? Waves in the open ocean are transmitting energy, period. That's it, just energy. Okay, they don't in the open ocean. Waves don't move water; they just move energy. Okay, so then we have three more questions. Let me see. Define wavelength, wave height, wave period, and wave base. So here it is, right here under wave morphology. There we go. So wave height is the vertical distance from the trough to the crest, right? Wavelength is the horizontal distance between two crests, right? Wave period is the time it takes for one wavelength to pass you, and wave base is the depth below which the wave is no longer, the depth below which the water is no longer moving due to the wave. And wave base is 1/2 of wavelength, not height. Okay, so if your wavelength is 10 meters, wave base is 5 meters. If the water is shallower than 5 meters, that wave is now dragging along the bottom, kicking up sand and all kinds of things like that. Okay. How does the longshore current affect barrier islands, right? And so here's the thing. Let me see. Let me find out where. Here we go. So how does longshore current affect barrier islands? It moves them, right? Barrier islands longshore current removes material from the upstream side of barrier islands, deposits it on the downstream side, and so the net effect is that the island moves. Around here, they generally move from north to south. Generally feet per year. This is something that we most definitely have to deal with. And then just one question about beach erosion. What's the effect of placing seawalls, jetties, and groins on the beach, right? And so here's the longer words. I can summarize it a little bit by saying, okay, actually I can summarize it by saying, okay, first of all, seawalls cause beach erosion, right? Seawalls, the minute the water hits them, the beach is gone. You can build higher tech seawalls, but you're never going to have a beach in front of it. You're just not. Jetties, groins, and breakwaters tend to trap sediment on the upstream side and possibly cause erosion problems on the downstream side, right? With a jetty, if I build a wall out into the water, that causes sediment to accumulate on the upstream side and erosion on the downstream side. A groin is just a jetty at the beach, has the same problem. A break wall is a wall running parallel to the beach. It shuts down the wave energy. You accumulate sediment, but downstream from that, you might have issues. Okay, and that's it. So if I didn't highlight it, if I didn't talk about it, it's not going to be on the test, okay? So I'm going to go and I'm going to compile this, and I'm going to upload the document. And if y'all have any questions, get with me. Okay, bye-bye.